Hi friends, so today I'm beginning Fortran lecture 8. Today I'm going to discuss double precision mathematics and we are going to use numerical derivatives to illustrate this concept. So I'm going to discuss finite difference derivatives, backward difference and central difference derivatives, and these derivatives play a very important role in a number of subjects, for example in optimization, in computational fluid dynamics, computational mechanics and so on. So there are many situations where you actually cannot obtain derivatives by simple differentiation as you do in calculus, and you have to resort to numerical derivatives. I'm Dr. Ganguly. Now let's start by looking at the simplest form of derivative, and that is the forward finite difference formula, which is given here. That is, the approximation to df by dx is fx plus h minus fx divided by h. Now, of course, those of you who have studied calculus know that this particular expression comes from calculus, and in the limit as h tends to 0, you actually get the derivative from its basic principles. Now, we will of course presume that h is a small number and then this particular definition holds. Now, if you are interested in the derivation of this equation, it essentially comes from Taylor series, and you can see it in my numerical differentiation video in the optimization playlist. I'm going to put a link to that in the description box and in the end screen. Now we are going to use this particular function to calculate the derivatives today, that is fx is 3 to the power x minus x to the power 9, and the derivative of this function is given by 3 to the power x log 3 minus 9 x to the power 8, where of course ln3 means that the log to the base e. Now this particular equation here has two roots, and I have obtained the roots in Math Question Bank 5 in the Math Mania playlist. I'm going to put a link to that also in the end screen and the description box. So let us now start looking at this more carefully. So we have this forward difference formula, and what we need to do is we need to calculate f at x plus h. So that would simply be this expression here, and of course we have the value, or rather the function for f of x, which is 3x minus x to the power 9. So essentially x plus h simply means that I substitute x plus h in place of x, and so I get this expression here. Now, the advantage of using these kind of formulas is that in case I do not have the exact solution or closed form solution of the derivatives, I can use this numerical differentiation. Now remember, there are many situations in problems out there, actual realistic practical problems, where you may have a computer code which gives you the value of f of x. In that case, what you can do is that you can perturb the different quantities. So for example, we are taking x here and we are perturbing it by some value h, and then we can obtain the derivative at the given point x. So of course this derivative is a local value of the derivative obtained numerically by perturbation, and h should be a small number. Now there is a trade-off between how small h should be and how large it should be, because if it becomes too small, then you start getting into some problems related to round off in computers because of the level of precision which the computer is using. And today we are going to look at that particular fact. What happens when we use single precision, that is 8 decimal places, versus double precision, that is 16 decimal places. But in general, h should be a small number. That's something most people agree on. So let us immediately write some simple programs here. So we have a program for the function. So this is a function subprogram, function f of x, and f is given as 3 to the power x minus x to the power 9, and then we end the function here. Similarly, we have this function here which is given as fd, that is the derivative of f of x, and that again is defined as 3 to the power x into a log 3 minus 9 x to the power 8. So remember, a log is the log to the base e. Now here these two functions are there, and then I need a main program. So in the main program, what I do is I choose a value of h, that is the perturbation, that is at 1 into e to the power minus 3, that is basically 0.001. I also take a value of x at which I want to find the derivative. So here I have selected x to be 1, and then I define the forward finite difference. I call it FFD as f x plus h minus fx by h. So having this particular function f as a function subprogram makes my life very easy, and I can write some nice piece of code to do that. Now, of course, I can compare this forward finite difference with the actual value of the derivative, because in this particular problem I know the actual derivative. We have differentiated this function, and so that will come to me if I use fd bracket x. So let's put this in the compiler and run it. And so here I have run this, and the values of course are h is 0.001, that's put in here, x is 1 is also put in here, and then I obtain the derivatives. I print out the forward finite difference derivative and I print out the exact solution here. Now of course you see these numbers are quite close, but there is some level of difference between them, and that is generally something which happens because you are doing numerical differentiation, so you are going to get some issues like that. Now what we do here is that we decrease the value of h, and generally you think that should give you a better answer, because what happens is that from calculus we know that the smaller h gets, the closer you are to the real derivative, because the real derivative is an instantaneous property at a given point. And so what will happen is that in the limit h should tend to 0. So in this case what happens here is that you get certain numbers, you again get a value of the finite difference derivative which is pretty close, but again it's not too near exact. And this particular difference which you are going to get in many cases is due to round off which is taking place. And round off happens because we are considering only 8 decimal places here. So you see the decimal places after these numbers here for the derivative, there are 8 decimal places here. So what starts happening is that fx plus h becomes very close to f of x. And so as h becomes smaller, these two numbers are increasingly smaller. And so the problem with that is that you are subtracting two small numbers, then you are dividing a very small number with a very small number. And so a lot of digits get lost out here, and that's not something which is good. And the extreme case you can see, if we use this kind of single precision math, which means we are using up to 8 decimal places in the program, and I set a h which is very small, so I choose h is 1e minus 10, then I essentially get 0 here, because what's happened that as far as the computer is concerned, fx plus h minus fx is basically 0, because the perturbation h is so small here that it does not even impact up to the 8th decimal place. So this certainly is not a correct result, and this is happening because of the precision mismatch which we have. So one of the ways to fix this is to use double precision math. And here what we do is that we can define the variables used in these programs, the main program and the function program, as double precision values. So we simply write double precision and we list all the variables here, such as h, x, f, ffd, fd. These are all the variables used in the main program, and also whatever variable we are using inside the function. For example, here we are using f and x. These are defined here as double precision, and here we are using fd and x, and these are again defined as double precision here. So I have just put the double precision values in pink to make it clear that these definitions are required to get that 16 decimal place calculation level. So now let's put this in the code, and you see all these variables are now defined as double precision. And again I use h is 1 into e to the power minus 10, and this time I get solutions which are very close, and you can see that now the computer is using up to 16 decimal places here because I have asked it to use double precision math. Now these kind of numbers are very accurate. Now there are some applications where you may not need to be too accurate. For example, if you are using optimization algorithms, then the derivative or the slope is simply guiding you toward the optimum point. The same is the situation if you are doing solution of nonlinear equation. In those cases, the Jacobian matrix or the slope will simply guide you toward the optimal point. But there are certain applications like computational fluid dynamics, computational mechanics, and so on, where you may be solving partial differential equations or differential equations. So whenever you are trying to solve differential equation, the discretization is such that the derivatives have to be as accurate as you can get, and in those cases this kind of high precision mathematics becomes even more important. But of course it does take some more toll on the computer in terms of all the different requirements and so on. Now, instead of using the main program to do the derivative calculation, let us try to create a function which calculates the forward finite difference derivative. So here I have created a function named FFD, and the input to the function is h and x, and the output of course is going to be the value of the FFD. Remember, the function simply outputs its value out, and this function encodes this formula here. So it defines FFD as fx plus h minus fx divided by h, so which is this formula here. So this function essentially calls one more function f, which we have defined previously, and also recall the function fd, which gives the actual exact derivative. So that's something we will use for comparison. So now we have a very small amount of code. We essentially define all the variables in terms of double precision, and then we simply read the values of h and x, and we print the values of h, fd, and ffd. So remember, fd is the derivative and ffd is the numerical derivative, the forward difference formula derivative. Let's put all this stuff into the compiler here, and then we print out these values. So again, h of course I have selected as 1 e minus 10, that's coming out here, and I have the finite difference value here, and I have the exact value here. So again, in this case you see that the numbers are pretty close, and so what you are getting is that you are getting a good accuracy as far as the derivatives are concerned. The program is also very clean because you have three nice functions here, and then in the main program you simply have a call to the functions involved. Now, one of the things we can do is that we can try to see what happens as the value of h changes. So that is a very important parameter whenever you are doing numerical derivatives, the perturbation h. And so let us do that. Let us put a do loop on top of h. And so I will do a do I is 1 to 10. I calculate values of h as h is 1 divided by 10 to the power I. So this will be 1 by 10, 1 by 10 square, 1 by 10 cube, and so on. It will keep getting smaller. And then I print the values of h, fd, and ffd. Fd is the exact derivative, ffd is the finite difference derivative. Let's do that, and here you see the values of h are given here and the values of the derivative are given here. And you can clearly see that as the values of h become lower, the derivative becomes better. Value of h around 1e minus 8 looks pretty good. And also you see if the value of h is very small like 0.1, then the derivative prediction is pretty bad in terms of forward finite difference formula. Now, before I leave, I will introduce you to two more extremely important derivatives, and these are the backward finite difference and the central difference. So let's start with the backward finite difference derivative. We will call it BFD, the acronym B, F, and D. And so this formula is given here, that is simply fx minus fx minus h by h. So in this case, you are seeing that you are at a current point x and you are going to the previous point here and you are subtracting h from x here. Now we can write a very simple function to actually include this particular derivative calculation, and I have done that here. I have called this function BFD. It takes in h and x and it returns BFD as the value of the function. I define everything in double precision and I put this formula here, that is fx minus f x minus h by h. Now remember, of course, the function f has been already defined previously. We are going to simply use that function. Now there is another derivative, the central finite difference formula, which is actually even more correct, or I should say it is more accurate. It is the most accurate among the three formulas I have discussed here. And so this is the formula for this particular derivative, that it's equal to f x plus h minus f x minus h divided by 2h. And so you get this function here which I have written out. So this function CFD has h and x as input, and it gives the value of the central finite difference derivative. Now in this case, of course, you have this function requirement at these 2 points. So one is part out by plus h, one is part out by minus h, and you have to remember to divide by 2 into h. So that's something which is important. Now if you want to see why this formula is more accurate, again it is coming from Taylor series. It's given in my numerical differentiation video. I'm going to put it in the end screen or in the description box. So let us now put these two functions here also. So I have put in the different functions for forward difference, for backward difference, and central difference derivatives, and then I have run this code here in the do loop. Now some of the remaining functions have gone below here, so they are not in the figure. Don't get too perturbed about that. And so you again see here that these values are printed out. The value of h, as it goes down, of course you expect the derivatives to be more correct, but you will see that the central difference derivative actually comes out to be more correct even at a lower value of h. So central differencing is generally recommended in most problems, and in fact people try to use central differencing wherever possible. So the question may come as to why would you require forward difference or backward difference. So there are certain situations in which that may be useful. For example, you may already have the value of the function at f of x, and then you simply have to perturb it by 1 point and get the forward difference value or the backward difference value. If you had the value at f of x and you had to perturb by 2 points, so you have to obtain f at x minus h and f at x plus h, then you would need to get additional function calculation. So this is sometime the case, but sometime it is not the case also. In some cases you simply have a graph, or let us say a function, and you have the function values at certain discrete points. In this case what would happen is that you would calculate all these values which are the internal points here of this function using central difference, because in these particular points you have access to x plus h and you have access to x minus h and the function values at these 2 points. But when you are at the starting point here, for example, you can calculate the particular derivative using the forward difference formula, because you would have access to x plus h and you would have access to x, the value at x. And similarly at the end point here you would calculate it using the backward difference formula, because you have fx here and you have f x minus h. So this is a situation where you can use all these three formulas for a particular set of points. So in many cases you have data which is available to you as at discrete points in the domain, and in those cases these formulas can be useful. So you can see, of course, that in many applications, for example, if you were ever doing computational fluid dynamics CFD, then you would use the central forward difference formula. Somehow the acronym has come out same, CFD, in both cases. So wherever you are looking for derivatives which are as correct as possible, go for central difference. If you are somebody who is okay with having somewhat less accurate derivatives, then you can go for the forward difference formula or the backward difference formula. So today's lecture you got introduced to not only the concept of double precision math, which is something very useful, but also to the important concepts of numerical derivatives and how to calculate them using simple functions. So the homework problem here is to write a subroutine which actually calculates all these three derivatives using the finite difference formulas for a given value of h and x, and in that case of course you can return all these derivatives through the argument list of the subroutine, and then you can compare it to the actual derivative values for different values of h and x, and that will certainly help to strengthen your concepts of subprograms such as subroutines, functions, and also how to integrate them with the main program. So that was the tutorial for today. So I think now you have enough knowledge of Fortran to write many programs out there. There are certain aspects of this language which I have not covered, which are somewhat deprecated, like the goto statement, the common block statements, and so on. And there are many features of Fortran 90 which I have not necessarily covered, and these may include, for example, possibility of recursion in functions. There are also different symbols which can be used for greater than, less than, and so on. So, of course, what happens in languages such as Fortran is that any of the compilers are backward compatible. So, you can always use the Fortran 77 features in the current compilers out there. And you can also use some of the newer features which I have included, for example, how to give variable memory for vectors and matrices. So, depending on your needs, you can use the Fortran 90 features or the Fortran 2003 type of features, or you can continue with the Fortran 77 features. And I would, of course, suggest that you don't use goto statements, because anything which can be done with goto statements could be done using do loop and if then else or if and if type of statements. So I'll end my lecture today, and make sure you see the videos which are on the end screen to continue your research journey.